Dear colleagues, we are happy to see again Professor Kauffman from the University of Illinois in Chicago. Uh, his title is about unitary braiding and topological quantum computing. I saw something about Majorana Fermions, but Luke can choose his own title as he wants.
Shall I begin?
Sure.
All right. Yes. So we will talk about Majorana Fermions as we go along. This is part of a series of talks. And so let's recall quickly what we had already done. I think I can leave this. No, maybe I'd better put this on full view for the time being. Let's see what happens. All right. So we're now on full screen and I'm adjusting something here. Um, okay. Right. Whoop. So you'll recall that much of this is joint work with Sam LaMonaco. And we had talked about hmm, some of this material before. I wanted to use the slides to recall for you some things, perhaps a little bit at random, just quickly. This is Schrodinger's equation, you may recall it. And in the history of things, Schrodinger came up with this equation trying to understand quantum mechanics, trying to create a theory of quantum mechanics. And after the equation had been discovered, people realized that the evolution of its solutions, the wave function, is unitary, which means that the integral of psi star, psi is a complex valued function on space-time, the integral of psi star is over space is time invariant. And that unitarity is often thought of in terms of finite matrices of transformation rather than full-bore differential equation evolutions. And we summarized quantum mechanics in this way, that there is a vector in a complex vector space. This would be the wave function if you were thinking of a Hilbert space of functions, but it could be a finite dimensional vector space as well, of a complex vector space, which means that the coordinates are complex. Um, the state of the physical system corresponds to a vector. Um, a physical process is a unitary transformation of those vectors. Where unitary you can take to mean, since we're thinking about finite dimensional vector spaces, is a matrix whose conjugate transpose is equal to its inverse. U star is the conjugate transpose of the matrix U, and U star U is equal to the identity. Uh, so, so that's a very abstract linear algebraic view of physical process. The state of the system is a vector with, of course, its many coordinates that correspond to the many possible specific observations that can be made, and transformations are unitary. That's what corresponds to physical process. And then, as I said, there are many coordinates to that vector, quite possibly. And here I've illustrated a vector with coordinates z1, z2 through zn. We are modeling in such a way that the EI represent possible observations that could happen. And so this state of the physical system is a state of possibility, and when you make a measurement, one of these possibilities becomes realized. And the probability that it gets realized is the absolute square of its coefficient. And we are talking about a unit length vector in the complex vector space. So the sum of the absolute zi squareds is equal to 1. And that means that each absolute zi squared can be thought of as a probability in a distribution of probabilities that adds to 1. So that's the measurement postulate due to Born and Jordan. Um, and this is the way the theory eventually crystallized for its users, written in a finite dimensional way. Um, and as you can see, if you wanted to think about what a quantum mechanical system would be like and how it would evolve, or how you would make an algorithm involving it, then you have the possibility of just thinking in terms of linear algebra. Of course, in order to actually make it in the world, you need to think about the energy considerations and many other things. But if you're only interested in making an algorithm, that would be some unitary transformation, and then seeing how the algorithm would behave when you observe it. And observing means looking at the vector distribution at the end and seeing with what probabilities it comes up with different outcomes. Then you can work algebraically, linear algebraically, and find quantum invariant quantum algorithms. And this is what Peter Shor, among other people, did in the 1990s and discovered a quantum algorithm in the sense of what I'm just talking about, uh, that can factor numbers faster than classical algorithms. And that was one of the reasons why people started to get very serious about developing quantum computers. And now we have some quantum computers, but we don't yet have them at a level that can perform Shor's algorithm. So I'm reminding you of these things. A qubit is an element in a two-dimensional quantum space. So there are two basis elements, 0 and 1, and we have complex coefficients, the sum of whose absolute squares is equal to 1. And a qubit is a probabilistic entity. If you observe it, you will get 0 absolute a squared fraction of the time and 1 absolute b squared fraction of the time. So that's the simplest example of this. Then we talked about some other examples, like the Mach-Zehnder interferometer with its mirrors that both transmit and reflect, and showed how we could think about some phenomena and how they're related to summing over paths in the resulting system involving the mirrors, like a system like this. This is the interferometer. The photon comes in here and it can be transmitted or reflected, then it gets reflected and so on, and you measure out here, and we did some examples like that. The examples are in the notes, and if anyone wants these notes, I think they've been made available to you before, but I can make them available to you again. And then we talked about another example of a quantum algorithm, which would be the quantum computation of the trace of a unitary matrix. Now, that sounds a little strange because you imagine that you already have the matrix. But in the physical system, you wouldn't have the matrix. You would know that the physical system behaved in a unitary way, and otherwise it would be a black box. So so here we can imagine that we have a matrix, but we are going to try to extract the trace of the matrix without looking at the matrix, only by using it as a transformation and making measurements according to my measurement rule, according to the Born rule. So um, we talked about that, and we talked about how you could do this with what's called the Hadamard test. And the Hadamard is like the mirror that transmits or reflects, and you add an extra line to the transformation so that you have what's called a controlled U, and you do some linear algebra here, setting this up, and then you make measurements on it, and those measurements are able to get you, both with good probability after a long time, the trace elements of the matrix, the diagonal elements of the matrix. I'm not going through the details of this, just reminding you what we looked at before. And then we talked about how uh, the entire collection of possible unitary transformations that you would like to make can be generated by very few transformations. And the theorems of this kind are: there is a 4 by 4 matrix, a 2-qubit gate, V is two-dimensional, G is a 4 by 4 transformation. There are various 4 by 4 transformations that you can use. And then you also need some qubit transformations like the Hadamard, and you can set up a collection of usable two-dimensional transformations that can be added in along with taking tensor products with this 2-qubit gate. And that's enough to make any quantum computer you need. So you need H, S, and T, that's a choice. And then you can choose a G that's good. And if you choose a good G and H, S, and T, then you can, using tensor products, generate any unitary transformations that you want, finite dimensional, hence make any quantum computer you would like. It's a little like the corresponding theorem in ordinary computing, where you realize that you can build any computer as long as you have a NOR gate and the notion of connecting wires together. This is almost as simple as that, but not quite. Now, one of the 4-dimensional gates that's usable is C naught, and this will I probably describe. No, I didn't. All right. Well, C naught, if you think about it the right way, and I'm just showing you a matrix, either flips the bit or it doesn't flip the bit according to another bit. You have 2 bits, so if the first one, 2 qubits, and if the first qubit reads a 1, then it will flip a bit. And if the first qubit reads a 0, it won't flip the other bit. So that's like controlling a knot. And we have a very nice theorem which is quite useful in thinking about quantum algorithms, um, which says that a gate is universal if and only if a gate G is universal, means I didn't say what that meant. I say that a gate G is universal if you can combine it with H, S, and T and making as many tensor products of spaces and transformations as you like to generate all unitary transformations. So the C naught is universal, but any gate is universal. Any 4 by 4 unitary transformation is universal if it's entangling. And entangling means that if you operate on a 4 vector with it, and that vector is a tensor product, it can happen that G of the tensor product vector is not a tensor product vector. It's not decomposable as a tensor product. We say that a 4 vector is entangled if it's not decomposable as a tensor product. And the Berlinskys proved this criterion for universality. Very nice theorem to use because it means that you can look around and choose a different gate if you like. And sometimes you can choose a gate that satisfies the Yang-Baxter equation, and that means that your topological computer that you're imagining building out of these gates would be partly topological, because the Yang-Baxter equation is the braiding equation, and we talked about that, and we
Excuse me, but does it have any use for topology? I mean, so we can take lots of other things which have nothing to do with Young-Baxter, and can you
yes,
extract any?
the idea of a use for topology would be to make quantum algorithms that compute topological invariants, such as not polynomials.
Oh, okay.
And in this case, in the case of the Bell operator that I've indicated here, that Bell operator is entangling, and it's a 4 by 4 matrix. Um, it's a universal gate, and it satisfies the Yang-Baxter equation. In this case, um, it calculates, if you think of it as putting it into braids and tracing it in the right way, it calculates a specialization of the Humphrey polynomial. But that means that I can formulate a quantum computer that calculates a specialization of the Humphrey polynomial. We can go further and talk about, as we will, fully topological quantum computers, and that they can calculate the Jones polynomial in principle. And that means that we have quantum algorithms that will calculate the Jones polynomial and sometimes also specializations of the Humphrey polynomial. They will calculate it. I don't know the estimates off the top of my head. They should calculate a bit faster than the usual apparently exponential calculations that are involved in calculating not polynomials. So you might imagine that in the future, searches for knots with Jones polynomial equal to one and things like that may be performed to very large crossing numbers by the use of quantum computers. Perhaps in 2050, we will find a knot with Jones polynomial equal to one by using quantum computers. Perhaps we will, perhaps we won't.
Actually, may I say something? Actually, I have some ideas how we can try to find this object.
Find what? Are you searching for
Yes,
gates
the note
or knots
with
with Jones polynomial equal to one? What are you searching
exactly.
for?
Yes. I just yes, exactly. I have some ideas how to particularly we can try to do it. So
Well, wait, I still didn't understand, Alina. Do you want to find knots with Jones polynomial equal to one? Is that what you're searching for?
yes, but I look in
I
the
mean, knots,
specific class
yeah,
in
I'm
specific class
sorry,
of
I
notes.
interrupted you. Start
In
again. You.
I mean, I try to find non-trivial note with such trivial Jones polynomial, and I prefer to look it in some very specific class of nodes that a little bit differ from the generally other all space of nodes. So yes, maybe I'm very sorry to disturb your talk. Maybe it's not was a good idea to.
Well, yes, I think that many of us have are interested in the search for non-trivial knots with Jones polynomial equal to one. And if you have thought about this problem, you might, like myself, have imagined a very large knot coming from some class which ought to have Jones polynomial equal to one, which you think is non-trivial. I've had that dream and thought I knew what one would be. But if I did come up with a proposal like that, it might be then a correlative question: how do I compute and prove that the knot is non-trivial? And uh, it might come to the situation where someone finds the example and proves that the example is non-trivial by using a very powerful computer.
Yes,
Could be.
exactly. Okay.
Yeah. Okay, so I'll continue. I'm reminding you that the Yang-Baxter equation is this equation about a tensored operator. You have R operating on V, tensor V to V tensor V, and you need this equation because you can think of the first braiding and the second strand as R tensor I, and then the first strand and the second braiding as I tensor R. And so you have R tensor I tensor R tensor I equals the other way round is the expression of the braiding equation in tensored matrices. And uh, and this is the Yang-Baxter equation and became very famous among us topologists because it was used by statistical mechanics people before the topologists realized that they could model many things with it. Early on, the Jones polynomial and the Humphrey polynomial, and then there are many, many families of non-invariants that can be based on this solutions to the Yang-Baxter equation. So one can ask for examples of unitary solutions to the Yang-Baxter equation that are universal gates, and there are some, like the Bell basis change matrix that I mentioned before, which will model the Humphrey polynomial, and some others. The simplest one I know is this little guy here, which as you see, is interchanging too, and it has a bit of a phase change here. But there are families of them, and when you make a computer that seems topological in this way, what you have done, let's go back a couple of slides. What you have done is you have chosen to make the G topological. But these parts are extra things in your diagrams. These parts are like what we were looking at in this diagram, where we saw on a single line in the diagram a certain transformation. So what this means is that at best you would be operating in braids, but there would be on single lines of the braid some extra transformation, some extra algebra on single lines of the braids corresponding to these. So it wouldn't be just happening that you would be representing the braid group. You would be representing some generalization of the braid group, not quite
Why
a pure.
generalization? Excuse me. Why is it a generalization?
It's a generalization of the braid group because single lines of the braids will have algebra corresponding to H, S, and T on them.
Okay. Okay.
I'll draw you a picture because this is worth thinking about. Sorry, I should have brought this up before. Paint. There. Okay. So what I'm saying is an element of the braid group looks like this. All right. And you could imagine that this goes to um, a tensor situation where you have an R here, and then you have an R here, and then you have an R here. And if R satisfies the Yang-Baxter equation, then this algebraic entity, which we could box up and call U, and it would be a little quantum computer, which takes an input here and outputs here, and you would measure here, would be a representation of the braid group. And so you could, if it was only the R's, get representations of the braid group involving the universal quantum gate. That's all fine and good, but you also need H, S, and T. And that means maybe I'll make notations from them, a little open. No, I won't. But I'll just let a dot mean H or S or T. So then your actual quantum computer might look like this. You see, with some extra transformation matrices that are happening on these lines. And that corresponds to a mapping from the qubit space to the qubit space, like that, right? So mapping from qubit space to qubit space, mapping from tensor product of qubit space with it, and then this generalized braid with these extra elements in it would map over to, of course, the corresponding thing over here, where there would be these extra transformations in the composition. So, so this would be a member of what I might call B3 tilde, which is equal to B3 augmented with H, S, and T. But H, S, and T don't have very pretty relationships with the R. You do not have, you would like to have some relationships. Maybe it happens that this would be equal to this. Probably not. You see? So you could, if you wanted to, investigate. I don't know that anyone has, a complete description of what this group is, this augmentation of the N-strand braid group with the HS and T.
Excuse me, do you have a
It's
text?
much more complicated than the braid group itself, and B3 tilde is not intrinsically topological.
Do you have a text where this group is defined?
No.
I would be happy to discuss it with you, maybe privately.
I have written about augmenting the braid group, but there is no structure known for this augmentation of the braid group. If you would like to investigate it with me, we could probably write a paper about possible descriptions of such things and whether or not they could be made topological. But that's the key question here is if you add these, does this still become topological? And would there be a topological interpretation of it? And we don't know a topological interpretation.
It looks like braids with parity. I think we wrote something with Fedosseev a lot.
Well, yeah, it could be thought of as something like adding parity, but it's more complicated than adding parity. You're adding some very special, specific kinds of matrices that you need. So this is one way of could braid group that way. You could call this partial topological quantum computing. Okay? Partial in the sense that as far as the braiding is concerned, that you can think of that as having a topological flavor, which means that there should be some deformations of the system that are not being affected by any that are not affecting the action of it as a physical system. That being the idea, right? The idea being that if you had a system, let's go back to my slides. I want to
I'm
go back
sorry.
to
May
my
I ask a question? Just a little question. Maybe could it be somehow related to, specific pinch points?
Could it be related to what?
Pinch points of pinch.
Pinch points?
Yes, exactly.
Well, what do you mean by that?
I mean, you told about the topological side of this story, and I just look at your picture and saw, for example, 4 points that moves, and so as we know from
Well,
the
let me
very
say
famous
something,
book
Alina. Let me say something.
Francis, the
I think
topological
I'm
book with
asking you to stop talking.
yes, sorry.
And one geometric point of view that we're about to talk about is the following, that you imagine a physical system that's two-dimensional, and that in that physical system there are entities that can move around, like these little vortices that you see here, these concentric circle entities. They can move around one another. And in the physical system, when they move around one another, there's a phase change in the physics. And so one has configurations of points that are moving around. We know that we can model the motions of configurations of points that do not touch one another via braiding. And if the physics that comes from such a system only depends on the way they move around one another, that it should encircle the other once or twice or three times, and just on the homotopy class of the paths that they move in, then we have something topological in the physics. And that means that if we can locate topological physics, then that means that the system can be perturbed without changing its quantum behavior. That would be topological quantum computing if we can measure enough about it. There are systems like that. Now, when you're talking about pinching, you may be thinking of interactions in the among the particles in the configuration space, like two particles merging to become one, and things like that. I don't know if that's what you meant by pinching. Did you?
Yes, just wait a second. I have exactly exact. Okay, so here we can define pinch points like okay. Here we have to define some. For example, homotopic maps of some surfaces to spaces, and I mean that if we would like to map one space to other,
Yeah,
and
I think
we
it's
can.
not going to work, Alina.
Um,
It's not going to work. I have to ask you to not try to do it. Sometimes when we have a mathematical concept, we can point to a picture that everybody can get. And sometimes it takes a long definition. And what you're talking about apparently takes a long definition.
I
So
mean,
we'll
it's
skip
like
it. We will
tetrahedron.
skip it and we will
Okay,
come back to this discussion at another
okay.
point.
Thank you.
But
Thank you
but
so
my
much.
the point I'm trying to make is that it is possible to imagine a physical system which is topological, and such physical systems, if we could measure them, would then give topological computing that is described entirely in terms of the braiding transformations. And there would be no extra strange local transformations that I had to put into my partial system. So that's one of the, what did I do here? Um, yeah, uh, get it back to normal size. So, so what I'm saying is that this is a stepping stone along the way, but it's always available that you might consider a partial system by finding some transformation that was topological. And the idea for the physics of that would be that that would mean that the system was a little less sensitive to perturbation, at least for these transformations. But a system that has the properties that I was indicating a few minutes ago is the quantum Hall system. The quantum Hall system is a system where you are looking at the measurement of current in a plate, and you have set up a potential across the plate, and you have current running through the plate perpendicularly to it, and it's in a magnetic field. And the electrons tend to become vortices around the field lines, and so they behave like like different kinds of particles, like collectives of particles rather than individual particles. And those collectives have braiding, so that you can set up a theory of quantum computing that's based entirely on braiding without any local transformations in it. Um, and the way this works in relation to things that we know as topologists is by using recoupling theory. So but I'm still describing it in the abstract. And now we're talking along the lines of things that we started to talk about before, but I'll go further. So I am doing it in the abstract right now. I imagine exchanging two particles, and the exchange of two particles is diagrammed by a little crossing, of course. I also imagine that I can indicate a measurement of the state of the two particles by allowing them to interact and finding out how they interacted. That will tell me about the state of the two particles. And it is assumed here that if the two particles interacted, then that if the two particles interacted by exchanging, then they would produce some phase lambda, e to the I little lambda. Um, and and so then you can think about braiding these two, or you can think about braiding these two. But when you braid these, but then you have to decide an ordering in which you're going to operate on them, part of our theory. So in our little theory of this, we're going to be able to measure these directly, and then we could measure how they behaved with regard to this. So if I want the state of this system, I measure these, and then I measure it with this one. So this means a measurement via an interaction for the sake of the theory. And you see that the direct measurement, which can happen, will give me a phase. But the indirect measurement, the next one, or asking what would happen if I braided these two, would require changing my point of view. If I changed my point of view so that first I measured these and then I measured this one, well, then I could get my information. I'm assuming that at the physical level, the only way I can get any information is directly. I have two particles and I let them interact. But that means that I have to think of sequences of direct interactions. I let these two interact, then I let it interact with this one. And if I choose one sequence, I get a space of possible interactions. If I choose a different sequence, I get a different space of possible interactions. Each sequencing corresponds to choosing a tree structure. And if I knew, now what I didn't show you here on this slide, and maybe I have a better picture on another slide, I think I do. Let's go past it to this. No, maybe I don't. Yeah, I wanted to show you this, but it may be in the other slideshow as well. Imagine that I had a particle P here, and this P can interact with itself either to produce nothing, radiation, or it can interact with itself to produce itself. So then in our tree structure, we would find either this element or this element. And then if we did it again, we interacted one more time, we would get another sequence. So in this case, we got a sequence consisting of star and P. And in this case, we got a sequence consisting of P and P. I can consider all the sequences that I can get out of a given tree structure. This is the picture I had in mind. So here's a big tree structure, just hierarchical. First I interact these two, then I interact with this, then I interact with this, then I interact with this, and so on. And then here's a sequence of things that could have happened. I could have gotten the particle back, then I got a nothing. Then I got the particle back, and I got the particle back, and then I got a nothing, and then I got the particle back. Nothing interacts with the particle always to produce the particle, so you can't have two nothings in a row. And you get sequences like these, which are sequences of P's or circles and stars, and you never have two stars in a row. If you count those sequences, how many such sequences you can make of P's and stars and no two stars in a row, you see you get a Fibonacci number of them. That's why this is called the Fibonacci model. And
by the way, there should be some categorification of Fibonacci. I mean, the Stashev polytope. Somehow we can, well, maybe not categorify, but make some topological structure out of numbers, Stashev polytope. And this will give us an action of the braid group, and this corresponds to what we call the group gamma. So there are lots of group action, braid group actions here, and
that's true. And some of them may be related to the quantum computing problem. It's possible. What you need to give me a little space to explain what I'm doing here, right? So what I'm saying is that we, corresponding to a given tree, we have a space of representation for the braid group. But in order to tell how the braid group is represented on that space, the space is the space of all these sequences. In order to tell how it's represented on that space, we need to be able to change bases to one of the other spaces to find out what the braiding transformations are. If I want to know how do I braid these, then what I do is I make the transformation to the other space. That's a recoupling transformation. Then I do the braiding operation there, and then I come back. And that gives me the representation of the sigma 2. So now I have sigma 1 already between the left two points, and I have sigma 2 from right 2 points to right 2 points by F inverse RF, where F is the change of basis. So by using all of these in that way, I get a representation of the braid group. And that representation of the braid group can be made unitary if you make the right choices. So let's go back to my original illustration here. One moment. There. So I have said this. But in order to do this, in order to make the this is detail about how you make it, but I wanted to show you this. Yes. So you see, you started to bring up things like Stashev. What you need if you want to make sure that you're getting a braid group representation under such circumstances where all of the different braidings are defined by changing basis into other spaces via the recoupling transformation, is the relationship between pentagons and hexagons and the recoupling. So this is part of the kind of formalism that you're talking about. If you start changing bases, then you find that this has to do with reassociation, because that's what recoupling amounts to in relation to the trees. Here's a tree, and you can think of this as AB times C times D, and this is A times BC times D. Reassociations correspond to the recouplings, and there is the usual 2 and 3 pentagon relation among such things. And if the basis changes satisfy pentagon, and if they then satisfy a nice hexagon relation in relation to the individual phasing braiding that we are using in a given vector space, if the pentagon and hexagon equations are satisfied, then indeed you get a braid group representation. Then all of these different braiding operations obtained by changing basis all fit together and actually give you, at any given tree, a braid group representation. So that goes all the way back to Joao and Street category theory related to braiding in the early 80s, but it applies, and it does apply to these physical systems. That has to do with the way conformal field theories work and Chern-Simon theories work. So there's a good theory related to the quantum Hall effect that says that we should be able to measure braiding if we had the right ways to measure it. And then we can build.
Excuse me, Lou. Alina has a feeling, and I also have a feeling, that the photography method is another way of interpreting the category theory. And I wonder whether the photography method has something to do with quantum Hall effect and whatever else.
Well, I don't know.
We will think.
We should think about it. We know this pattern. This is an old pattern, very pretty pattern. that if you want to get a representation of the braid group from a braided monoidal category with recoupling like this, then you can do it if you have this coherence. You need the coherence of having the pentagon and hexagon relations. Um, and what you do with the G groups and so on seems reminiscent of this, but it's being done in a different way. So keep thinking. We should talk about it. I agree. But this is one proposal for getting topological quantum computing, and at the combinatorial level of Jones polynomial and recoupling theory and Temperley-Lieb things, we can make a model of this. I'm not making a physical model of it, I'm making a model of the recoupling situation. So you do that by using Jones-Wentzel projectors and putting them together into vertices to form trivalent vertices, like you can take two projectors, two line projectors like this, and put them together and get a projection like this. And this one will model a very simple kind of particle interaction. If you think about what are the possible vertices that you can make from a two-line Jones-Wentzel projector, these are single lines in the braiding, and you're looking at two lines here, and this is a two-line Jones-Wentzel projector. If you multiply it by itself, get itself, and if you concatenate it with a turnaround, it'll be zero. Um, what kind of vertices, trivalent vertices, can you make? Well, you can make one like this, where the lines add up this way, and that looks like particle interacts with particle to produce particle, like that. Or you can make it this way, and there is no exit line, and that looks like particle interacts with particle to annihilate. And then, if you work at a fifth root of unity like this, you can forbid the only remaining combinatorial possibility. And so we have an example of a very elementary mathematician's particle which interacts with itself either to annihilate itself or to produce itself. And then you can look at the tree structures for that and all of the braiding that you can do with that. And you can do a lot with that. You can model specializations of the Jones polynomial and so on. And this actually corresponds theoretically to one of the possibilities for the quantum Hall effect. But the problem here is that in our theorizing, we modeled our interactions of particles by these recoupling vertices. That corresponds to tensoring certain representations in the conformal field theory. But no one knows how to make those kind of measurements. So, in reality, there is a reality of the quantum Hall effect, but people don't know how to make those kind of measurements. They would have to make other kinds of measurements, and so far, no one knows how to make these phase measurements that would be needed in order to make an actual quantum computer that corresponded to this. The people at Microsoft, spearheaded by Michael Friedman for many years, were trying to do this. Kataev, and other people. But so far, no one has actually made this model in physical reality. But maybe after a few more Nobel Prizes, we'll see that this model can actually be physically realized. The model as something to tinker with mathematically, if you like Jones polynomial and Temperley-Lieb recoupling, is very nice. The one that I was showing you with only one simple particle at certain roots of unity, the basic change of basis matrix is this, where tau is the inverse of the golden ratio, and the phases, the basic phases involved are in the R matrix there below, and one can then proceed to formulate the general case of such models where you use the formalisms of the recoupling theory. In a more general model, you would have A strands rather than two strands, and you would have the Chebyshev polynomial that evaluates the trace of a projector. You would have thetas, theta graphs. You would have tetrahedral graphs. You would have 6J coefficients and the apparatus that comes along with that. Um, and 6J coefficients can be evaluated in terms of tetrahedral and theta graphs, and you get more complex phases like this, and you can work out using the recoupling theory what the formulas will be, and with the help of that, these are just the recoupling formulas rewritten to make sure that you get unitary transformations, and then if you use roots of unity, you can use unitary representations of the braid group from the Temperley-Lieb recoupling theory, and it's sufficient to produce unitary transformations for quantum computing. It's a generalization in this form of the universal gate theorem that I mentioned before. You can, in principle, do all your quantum computing using the Fibonacci model. But no one knows how to make a realization of that. But that would be true topological computing if you had it. And then you could compute things like Jones polynomials by basically tracing them from a Platt representation, for example, which is what I'm indicating here. There are various schemes for doing that. The reason I showed you this one is because if I had a Platt closure of a braid, then I think of cutting the caps on the Platt open at the top and making measurements at the bottom, and then I'm looking at the braid in the middle as the basic unitary transformation in the quantum computer that's going to compute the braid. So that's the way things look in that form. So I've been a bit sketchy about that, but the questions are, will these models really be used? They may eventually be used if people can do more physics. And now we are at a point near the end of the talk, but I want to tell you about the other point of view, another point of view, which has to do with um, fermions and what are called Majorana fermions. So this is another story. It's related a little bit to part of what we already talked about. Majorana, a long time ago, um, proposed the existence of a particle that would be its own antiparticle. So did we in our model that we were using before, our P there, that was very simple and came from the two-strand Jones-Wentzel projector. And that means that um, you could call some of the particles in the quantum Hall effect Majorana particles. But Majorana was thinking in a more general way, thinking about fermions like electrons, and imagining that he could have a particle that was its own antiparticle, and maybe the neutrino would be its own antiparticle, you see. And he wrote down a version of the Dirac equation that could be used to model such things. So we're going to think about that, and I'm going to skip some things that are in this slide because we're running out of time. Uh, so here's the thing. A fermion, a Majorana fermion, has an algebra associated with it. And I have to explain to you why I would think about this algebra, but I'm going to show you the algebra first because it's very simple. Um, I'm going to have A and B correspond to Majorana fermions. And we're going to have that A in the algebra of them, A squared is 1, B squared is 1, and they anti-commute. Now that's a simple Clifford algebra, very small Clifford algebra. And so what I'm telling you is that Majorana fermions are associated with Clifford algebras. But why should fermions have anything to do with Clifford algebras? For that, you need to know a little bit about the story about standard fermions and what kind of algebras they're associated with. And it turns out that associated to a standard fermion is an annihilation operator that will kill it off called F for me because of my poor alphabets in this slideshow, and a creation operator F star. And and if you apply F twice, it's zero. And if you apply F star twice, it's zero. But FF star plus F star F is equal to the identity. And I'm not motivating this very well for you because of time considerations, but you can think of FF equals zero and F star equals zero as corresponding to the Pauli exclusion principle, which says that two fermions in the same state don't exist together. And the other one is that these are two ways of creating FF star and F star F. Um, they, the two ways add up to one. So that's the algebra of a fermion. And if you were to, in this last 5 minutes, just accept that fermions are associated with such an algebra, then I can show you how Clifford algebras could be imagined to come in. And I'm going to do it just by abstract algebra. Suppose that you had U and U star, and you had the Clifford algebra, and you wrote U is equal to A plus IB, I being the usual commuting square root of -1, and U star is A minus IB, complex conjugate of U. And now you played a little algebra game with it. You multiplied U by itself. A plus IB times A plus IB. And remember, things don't commute. So I get A squared, but I get minus B squared because I does commute with things. And then I have IAB and IBA. But AB plus BA is zero in the Clifford algebra, and A squared and B squared are equal in the Clifford algebra, so U squared is zero. Oh, so you see, the Clifford algebra provides a way to create a fermion algebra. Two Clifford elements, AB, create one fermion. And U star equals zero as before. And if I take U star plus U star U, well, that's the same as U plus U star squared because the extra terms U squared and U star squared go away. And that's 4 times A squared because U plus U star is equal to 2A, and I get 4. So up to normalizing things a little bit, I get the fermion algebra out of a Clifford algebra. So up here in the level of playing with algebra, you see that two Majorana fermions identified as Clifford algebra elements make one electron. So you could speculate that an electron, a fermion, is somehow related to two particles that are bound together. Like quarks make protons, two Majoranas should make an electron. What a nice idea and what simple mathematics to play with in relation to it. It might be a false physical idea, but it's certainly understandable idea. So that says that a row of n electrons could be regarded as a row of 2n Majorana fermions. And and then there has been a lot of work since around 2012 of experiments that suggest that Majorana fermions, in the sense that I'm talking about them, can be detected in nanowires. That means very thin wires at very low temperatures. And the detection would have to do with thinking about a long wire with a lot of electrons in the row, and each electron is a pair of Majorana fermions, but they couple like this, and you would be left with a free Majorana fermion on the left and another free one all the way over on the right, and that will result in a certain kind of correlation that you could imagine measuring. And there's a famous paper by Kitaev a while back that details how that works. And then a paper that I can understand and any topologist can understand by Mr. Ivanov. And he worked out then what happens if we start exchanging the Clifford algebra elements, thinking of them as particles. And he discovers that there are very nice simple braid group representations related to the exchange of Clifford algebra elements, related to the exchange of fermions. So, um, I'm going to show you that. But as I said, the experimental idea is you have this conducting wire, very thin, low temperature. You measure the correlation between the ends of the wire. When you see these ads or news announcements by Microsoft that they are about to do topological quantum computing, they're referring to the fact that they off and on keep thinking that this experiment has succeeded. It's probably going to be some years before, even if this experiment succeeded, that reliable measurements can be made for making quantum computers. But here's a very nice Clifford braiding theorem, which I've abstracted from Ivanov. And we'll stop there. I'll show it to you for a moment and then we'll stop. You take a row of Clifford algebra elements, um, and then you form a new element, and they anti-commute with one another, and they all square to one, okay? And then you take these algebra elements, 1 plus ck plus 1 times ck divided by the square root of 2. You can check that the ck plus 1 ck squares to minus 1. So this looks like 1 plus I over the square root of 2, and it has order 8, right? But these guys form a representation of the braid group. Very nice representation of the braid group coming out of the Clifford algebra. And that means that underneath fermions, underneath electrons, there are representations of the braid group that happen here, like that. Um, these are nice exercises to do. You can prove to yourself that indeed the Clifford algebra relations are giving rise to a representation of the braid group. And the simplest case is where you took the quaternions I, J, and K and formed A, B, and C like that. So those are replacing my CK plus 1 CKs. And then you can check that this gives you a representation of the braid group. ABA equals BAB, and so on. That's the simplest example I know of this. And so you get representations of the braid group that are related to the Clifford algebra that are of order 8. And then Ivanov had a very interesting idea that makes things even simpler. Um, he said, all right, but I'm going to think of these particles as being acted on by the braiding, and I'm going to see how they get moved around. So I'm going to take the braiding operators, which are represented by Clifford elements, and I'm going to conjugate them. I'm going to take tk of x on the span of the Clifford elements to be the conjugation by tau k, the braiding operator. And now, instead of being order 8, the order drops, and the braiding is very simple. The braiding is as simple as this, that when two of them interchange, then one of them gets multiplied by a minus sign and the other does not. And this leads to a puzzle that one ought to think about, and I'm going to quit at this point. You do see, I'll tell you the puzzle, but you see that now we could think about using these braiding operators to make quantum computers, except that one doesn't have a complete story like the Fibonacci model. One has some ideas of configurations of fermions and braiding operators, and maybe one needs local operators as well in order to build the quantum computer if you could. So we're back to partial. Um, and that's the present story in the nutshell. But the part that I think is worth thinking about for a mathematician is, a topologist particularly, is that what we have here is an augmented belt trick. When you take a belt between the two particles and you exchange the particles, you get a 360-degree twist in the belt. If you like the belt trick, you can think of the 360-degree twist in the belt as corresponding to the phase change in the system that occurred when they braided. But in Ivanov's representation, the braiding is associated with only one of them. The phase is associated with one of them, not with both of them. That's an extra ingredient, and it is that extra ingredient that makes for a braid group representation here and not just a phase change. Now, we usually think of the relationship of the belt trick and the braiding by looking at the double cover of SU2 to the rotation group in three-dimensional space. But here, it's not clear how some generalization of the double covering is focusing the phase change on one element and not the other. There is some missing topological geometry right here that might be obvious if one thought about it the right way. So I leave you with that puzzle and stop for the time being. Okay?
Okay, Lou, thank you very much for a nice talk. We are always happy to listen to your talks. Are there any further questions or comments? Well, I will be very happy to look at braids with further structures. I will be very happy to look at stashification of everything. Maybe stashification, I think.
Yes, Vasily. I think it would be very good to discuss that. So you can you have interrelationships with the groups G and actions on the Stashev polytope.
Not quite G and K, but gamma and K. It's a similar thing.
Gamma.
Yeah,
Mm-hmm.
yeah, I do. Yeah, I do. Well, I have actually, some 2 or 3 years ago, I was talking to Jim. I don't know how he is now. And actually, I gave a talk for at his seminar, Jim Stashev. And maybe he gave a talk at our seminar. I don't remember.
Right.
Yeah.
Well, maybe you would like to give a talk about this aspect in the quantum topology seminar in late January.
Certainly yes, certainly yes. By the way, I have a student, Louis and Joe, and he's here now, I think, and he can give a talk about many things related to virtual knots and virtual knots approaches to classical knots.
Yes, that would be very good too. So we'll do some email exchanges and figure out time.
Sure, absolutely, yeah. Great.
Yes, yes,
Yeah.
Professor. I will when I write it more perfectly, I will send to you. Thank you, Professor.
Oh, very good. That would be
Okay.
great.
And
Okay.
may I ask a little question? It's just about, do you know the notion of the Breen knot? I mean, there is some kind of while knot that made by that constructed from the infinite number of stitches of knot, and it looks like exactly the dynamics of braiding points. So I mean, it's this object has the name Breen knot.
How do you spell that?
BRIN, Breen.
Bryn knot.
Mm-hmm.
Well, of course, there are lots of wild knots, so I'm not familiar with this one, it seems. What is the property of it?
It's some maybe it's better to answer this question later in the personal email. Okay?
Oh, okay, that's fine.
Because
Sure.
yes, it's be more constructive, I think. And thank you very much for very interesting talk.
Thank you. I look forward to talking again. Thank you very much.
Any further questions? Any further questions or comments? Okay, so let's thank the speaker again. The talk was great.
Thank you.
Okay.
Thank you.
Thank you. Yes,
I have
yes.
something partially in my mind that isn't fully developed that came out of Alina's suggestion of pinch point and also this about the generalization of the braid group. Then on the algebra side, we're thinking of taking some quotients, but also topologically, there is the notion of taking quotients or forming a quotient space. And when two particles come together in their interaction so that they are no longer separate in space, then that's kind of like in a sense resembles quotient in a topological space. Does it not? And can this thought be maybe further investigated?
Well, let me share the screen for a moment. I point out to you that when we originally were thinking about quantum invariance, we were thinking in the following kind of way, right? That we might have, not a very interesting link. We might be thinking of something like this, yes, where we think of a process going on, time going up the page, and then what happened was that two particles got created, and then two particles got created, and then after this point, some braiding occurred among them, braiding. And then two particles annihilated and two particles annihilated, right? And that's the story. And then there is an operator for this, and there is an operator for this, and there's a braiding operator for this. And in the general case, the braiding may be mixed up with the creations and annihilations. But if you think in terms of configuration spaces, then that means that you started with nothing in your configuration space, but then after a little while, there were a critical point where there was one, but then a moment later there were two, and so you had a creation, and so on. And so you allowed beyond the braiding of points in the configuration space, you allowed the creation and annihilation of points. And that is the physical picture that you have behind the quantum link invariant, which has operators for each of those. But I don't know how to Well, I do know how to write mathematics that gives me link invariance, but I don't know very much about the physics of thinking about adding to the configurations, creations, and annihilations. So I think that speaks to what you were saying.
May
and
I
I'll stop.
ask, is it somehow related to the four-dimensional sphere and for the quotient of CP2 by the group of automorphisms of complex numbers, and that the fact that these quotients is actually four-dimensional sphere, and it's maybe somehow related with quantum Hall effect and Hopf vibration.
Well,
Okay.
as I said, the basic one is SU2 mapping down to rotations of three-dimensional space, and that is related to the Hopf vibration. You have two maps from S3. S3 goes to S2 by the Hopf vibration. S3 goes to SO3 by the double cover of the rotation group.
Okay, thank you very
There's
much.
more there for sure.
Okay, any further question? Yeah.
I was thinking when we have layers and you have the
When you have what?
creation, when we had the layers, first no particles, then only one particle, critical point, then two particles. Could
Yes.
we consider, for example, transformation of topological spaces or a continuum of topological spaces, and then in some sense, if we were to take the quotient when there are two particles, it's not exactly the same as having only one particle, but we could merge or transform one layer with that identification, with taking quotient progressively to only one particle being there. So it's kind of like maybe, I don't know, something resembling a deformation of space in some sense, and then trying to model the particle interaction through the deformation of spaces. Maybe it's unclear. I don't know.
Keep thinking.
Okay.
Yeah.
Okay, I think that's all for today. So thank you very much for coming, and I think you can discuss everything personally.
Yes, we'll keep talking. We'll keep thinking. Right. Thank you very much. I'll leave now. Yeah.
Okay, thank you.
Thank you very much.